All right, hello, Union High School Pre-Calculus. I hope you all are doing well, staying safe and sane. My name is Mrs. Peterson. I teach Pre-Calculus alongside Mrs. Bybee, Miss Miller, and Mr. Thomas. And we are going to be diving into limits today. So I'm going to do my best to kind of direct you as to what I would like for you to write down in your notes and what you can just listen to. So for now, let's just read this slide together. So graphical limits, a function's value, and remember when we're talking about f of x, we are talking about its y-coordinate. So if its y-coordinate approaches a number L, as x approaches a value c, from both the left and the right, we call L the limit of f of x as x approaches c. Okay, we've talked a bit about limits already, but I want you to write down the word approaches and limit. Okay, those are the two words we really need to connect. So when we're talking about a limit, we're talking about what number is the y value approaching as the x value is approaching a certain number. Okay, so approaches and limit. The other thing I'd like for you to write down is this notation here. Okay, so this is said, and I would like for you to write this as well. Let me give you a moment to copy that down. So that's the math notation. This is how we say it in words, and I'd like for you to write these words down as well so we know we're saying it correctly. So the limit as x approaches c of f of x is L. All right, so that's how to say it in words. All right, the following needs to be true for the limit to exist. And just so that we're on the same page here, L and C are constants, okay? Those are just numbers. So L is the number your y values are approaching, and C is the number your x values are approaching. So this has to be true for the full limit to exist. The limit as x approaches c from the left-hand side, and we denote that with a little minus superscript of f of x, has to be equal to the limit as x approaches c from the right-hand side. Okay, and you may have seen this notation before as well, but let's go ahead and put these in our notes and make a note to ourselves that this is the left-hand limit, and this is the right-hand limit. Okay, and I know this is a lot of notation and vocab, but we're going to do a few examples to make this a bit more concrete here, okay? Alrighty, let's try some examples. All right, you do not need to write this down, but just kind of so you know where we're going, we can evaluate limits in 3 different ways. We can evaluate them graphically, which is what we're going to talk about today. You'll practice it tomorrow and Wednesday. We can evaluate them numerically, which is with a table. And that's what we'll be doing towards the end of this week. We can also evaluate algebraically, also known as analytically, which is where we give you f of x, your function, as like an equation. So like f of x equals x squared, okay? And we'll be doing that next week. And these are the 3 ways we can evaluate limits. Again, you don't need to write that down, just kind of FYI, this is where we're going, okay? What I would like for you to do now is pause the screen and copy this line in your notes. It's a decreasing line, y-intercept 2, x-intercept 1. All right, go ahead and pause and hit play when it is drawn. All right, so we want to find all 3 limits as x approaches 1. And by all 3 limits, we mean the left-hand limit, the right-hand limit, and the full limit. And it says right and limit notation. So let's go ahead and just sort of prep our notes for that, and then we'll go and find those 3 limits. So we're going to find the limit as x. Remember, we're approaching 1 from the left. Don't forget to put f of x here. We're going to assume that this is the graph of y equals f of x. If you leave that f of x off, we call that a naked limit when we're grading AP exams, and you do lose points for that on the AP exam. So really get in the habit of making sure you've got your function in there, okay? So we're going to do the limit as x approaches 1 from the left, the limit as x approaches 1 from the right of f of x, and then we're going to do what I call the full limit. And remember that the full limit only exists, if I come back here real quick, the full limit only exists if the left and the right hand limits are the same, okay? All right. So what I'd like for you to do now is actually draw a vertical line at what our x value is approaching. Our x's, remember, are approaching 1. So I do a dotted line, like a vertical guide, at x equals 1, okay? And what we're going to do is approach that vertical wall, that purple line, from both the left and the right-hand side, okay? So let's start with this coming from the left. So I'm going to grab onto that function somewhere to the left, there we go, of that purple line. And then I'm going to start approaching that purple line. I'm going to get closer and closer. So you can see my x values are approaching 1 from the left. Can you tell what the y values are approaching? Yeah, the y values are approaching 0. So I can put that this is equal to 0. All right. Okay, let's do the same thing coming from the right-hand side. So I'm going to grab onto the function somewhere to the right of that purple wall. And now I'm going to start approaching the wall. So you see I'm hanging on to that function, right? But I'm coming from the right-hand side this time. And you can see as I'm coming from the right, can you tell what the y values are approaching? Again, the y values are approaching 0, correct? So this limit is also equal to 0. All right, now let's talk about the full limit. Were your left and right-hand limits the same number? Yes, they were. So that means that the full limit is also equal to that number, okay? If they're different, the full limit is not going to exist, and we'll talk about that in a moment, okay? So these two numbers have to be the same for this limit to exist, alrighty? All right, let's try another example. Can you do the same thing for me here? Sketch this graph in your notes and then pause. This is going to be a concave up parabola with y-intercept at 7. Vertex is at 2, 3. However, the vertex is going to be an open hole. So go ahead and pause your screen and graph that. All right, so now we want to find all 3 limits as x approaches 2. And again, by the 3 limits, we mean the left, the right, and the full limit. We want to write this in limit notation, so let's go ahead and prep our notes for that. We've got the limit as x approaches 2 from the left-hand side, the limit as x approaches 2 from the right-hand side, and then we're going to have the full limit. Okay, and let's do the same thing as we did last time. Let's go ahead and draw a guide, a vertical dotted line at x equals 2. And let's start approaching that guide from the left first, okay? So I'm going to grab onto the function anywhere to the left of it, okay? Ooh. Could have picked any location here as long as I was to the left. And now let's start approaching that purple line. Can you tell what y values I'm approaching? What y value I'm approaching? Yeah, I'm approaching the y value of 3. Remember that we tie that word limit to the word approach, okay? Do I actually land at 3? No, but this is the limit. This is what I'm approaching. So the open circle, that hole, does not affect the limit, okay? That's very important. So the limit here coming from the left does exist. It's 3 because that's what I'm approaching. Okay, let's try coming from the right-hand side as well. So I'm going to grab onto the function somewhere to the right. All right, and now I'm going to approach that purple line coming from the right-hand side. And you can see we're still approaching y equals 3. So the right-hand limit is also 3. And since the left and the right-hand limits are the same, the full limit also exists and is 3. So again, since these two numbers were the same number, same value, the full limit is going to be that number as well. Alrighty? Okay, so far 2 examples, our limits have existed. All 3 limits existed in these 2 examples. So let's start looking at some cases where the limit fails to exist. Alrighty? So do me a favor, pause your video and copy that whole screen for me. Okay, so you can see here on the right-hand side, we're looking at or around x equals 2 for each of these, okay? So where would we draw our dotted guide or our dotted wall? We're going to draw it at x equals 2, okay? And keep in mind, limits are what? They're what we approach, okay? Not necessarily what we land on. It's just what y value are we getting close to. All right, so let's start with the left-hand limit. I'm going to grab on to the function somewhere to the left of that dotted wall, and I'm going to start approaching the dotted wall. What y value am I approaching? Yeah, actually I'm on y equals -1 that whole time. We're going to assume each tick mark is 1. So the limit as x approaches 2 from the left is -1, okay? All right, let's try the same thing coming from the right. So I'm going to grab onto the function somewhere to the right of that purple wall, and I'm going to start approaching. Does the limit exist here? It does. The right-hand limit does exist. Remember, the open circle does not affect the limit. It's just what y value am I getting close to, and what y value am I approaching. In this case, I'm approaching y equals 1. Okay, now you can see here that the full limit is going to fail to exist. Why? Well, because the left-hand limit and the right-hand limit are different numbers, okay? So when that happens, the full limit does not exist, and it's common mathematical notation to just put DNE for does not exist, alrighty? What do you think the most common mistake in calculus is for this particular example? So the most common mistake is to say, oh, the full limit is y equals -1, because that's where the closed circle is. But remember that closed circle has nothing to do with limits, right? The limit is just what are we approaching, and we have to be approaching the same y value coming from both sides. All right, so in this case, since we're approaching different numbers from the left and the right, our full limit does not exist. Now, what in the world does that closed circle mean then, right? So let me clear some of this here. Okay, so if we take a look at this original graph, what does that closed circle mean? Well, the closed circle affects the function value, right? So this tells me what the function value is at 2. So when x is 2, y is -1. That's what the closed circle tells me, right? So function value is what is happening exactly at that x value. Limit is what's happening around that x value, okay? All right, let's just look at a couple or a few other instances where the limit can fail to exist. All right, again, do me a favor, pause the video and copy the screen. All right, so our second instance where a limit can fail to exist is if f increases or decreases without bound. In other words, it approaches positive or negative infinity, also known as a vertical asymptote. Okay, so if you'll take a look at the right-hand side here, you can tell that we're dealing with x's approaching 0. I don't know if you can hear my kitty meowing in the background. So what I'm going to do is draw my guide at x equals 0. All right, so let's take the limit coming from the left-hand side. So again, I'm grabbing onto the function somewhere to the left. Once again, I could have chosen anywhere to the left as long as it is approaching this wall. So what happens as we approach from the left? Oh, that goes on forever, right? So my y values are approaching positive infinity. So I can write that the limit as x approaches 0 from the left of f of x is infinity. Now infinity, trying to hold a cat and write at the same time now. Infinity is not a number, so it is appropriate to just say that the limit does not exist. That's fine. If you look at our note here, anytime f of x approaches plus or minus infinity from any side, the limit is said to not exist, because again, infinity is not a number, okay? Similarly, if we try to come from the right-hand side of that wall, so if I grab onto the right, I approach that dotted guide. This time my y values are going down forever. So the limit coming from the right-hand side is negative infinity, but it's also fine to just put d and e here, okay? Now the full limit is certainly d and e because you've got different signs on your infinities here, right? So the limit as x approaches 0, the full limit here is d and e, all right? All right, those are your most two common ways where limits will fail to exist. So either what we call a jump, where your left and right exist, but they're different, or a vertical asymptote, okay? So where your limits are plus or minus infinity. All right, a couple more ways, though not as common. Limits can fail to exist if they oscillate back and forth, okay? So you do not need to copy this one. Let's just sort of talk through it. This is probably the most common example to show a function that oscillates between two fixed values as x approaches c. It's sine of 1 over x. And let's see if my Desmos will load here. Yay. Okay, so here's more of a interactive view of this function. So do you see how as x approaches 0 from both the left and the right, my y value is just going to jump back and forth between -1 and 1. So in this case, all my limits are d and e, okay? So coming from the left is a d and e, the right, and then of course the full limit, okay? Not super common, but that is a way a limit can fail to exist. All right. Okay, do me a favor, pause the video, copy the screen. Okay, so our fourth and final way that a limit can fail to exist is if f of x does not exist on one side of the x value that the graph is approaching, okay? So take a look at the questions above the blue bar there. Notice they're all dealing with x equals -1. So I'm going to draw my guide at -1. And what's going to happen if I approach from the left is there's nothing to grab onto there, right? So in this case, my left-hand limit does not exist. And by the way, that tells me automatically my full limit does not exist, right? But let's go ahead and find the right-hand limit first. So I'm going to grab onto the function somewhere to the right of that wall. And as I approach, can you tell what my y's are approaching? Yeah, my y's are approaching +1, okay? But since the left-hand limit failed, the full limit is going to automatically fail. All right? All right, let's take a look at the questions on the bottom. What I'd like for you to do is actually pause the screen and try those questions on your own. All right, let's see if we're back here. See how you did. Let's go ahead and move our dotted guide to x equals 0 this time. All right, if I want to approach that guide from the left, I don't have a ton to grab onto, but that's okay as long as I have what's called a neighborhood, we're fine. Okay, so if I approach from the left, we are approaching what y value there? We are approaching 2. And if I approach from the right-hand side, looks like we are also approaching y equals 2. And since the left and the right are the same number, then the full limit is also that value, okay? And in this case, the function value is also 2, nice and continuous there, all right? Okay, so just a recap, the ways in which limits can fail to exist. You can have a jump, so that's where the left and right-hand limits exist, but are not equal to each other. Now it's like in that example. The second way is basically to have a vertical asymptote. Okay. The third is an oscillation. And then the fourth is f of x itself does not exist on at least one side of the limit. Okay. Alrighty. Okay. Go ahead and pause the video, copy the screen, and see if you can fill in the blanks. Okay, so an open circle, and see if you got this, does not affect a function's limit, only the function's value. Okay, so remember, limit is what y value we're approaching. Function value is exactly what the y value is at the indicated x value, okay? All right, so what is the closed circle there, essentially? Okay, let's try one last example. Again, pause the video, copy your screen. Okay, if you haven't already, go ahead and pause again and try to answer each of these questions. All right, so let's see how you did. The limit as x approaches -2. Let's see here. Right there. So that limit is the same coming from the left and the right, and the y values, we're approaching 0 from both sides, okay? All right, let's move our guide right to that asymptote. Well, we know that at a vertical asymptote, the limit does not exist, right? So this is a D and E. Okay. All right, moving that guide to x equals 0. Does the limit exist here? Yeah, the limit is going to exist because look, we're approaching the same y value coming from the left and the right, okay? We're approaching 2. Now, what is the function value there? The function value is this closed circle here. So f of 0 is 1. All right, let's move that guide to x equals 2. Does the limit exist here? No, it does not, because look, the left-hand limit exists and the right-hand limit exists, but they're different from one another, and that's one of our instances where our limit fails to exist. This is what's called a jump discontinuity. You'll learn more about that next year, but the limit here, the full limit here, does not exist. Does the function value exist? Yes, it does. I have a closed circle there, so f of 2 is 2. All right, let's move that guide to 4. Does the limit exist here? It sure does, because we're approaching the same y value from the left and the right. We're approaching y equals 0. However, the function value does not exist. See, there's no closed circle for x equals 4, so function value not exist. Remember, function value is what is y at that x value. Limit is what is y approaching around that x value. Okay? Alrighty. Well, we miss you very, very much. Please don't hesitate to reach out to us if you have any questions. We just ask that you take notes on this video today, and then tomorrow and Wednesday you'll have a couple My Math Lab homework assignments on limits graphically. So we will talk to you soon. Have a good day. Bye.